welcome to Physics with Mr. McQueary. Today we're going to be dealing with Newton's laws of universal gravitation. We've talked about Newton's laws before. This is just one of them, and it deals with basically the gravitational pull between any two objects in the universe. So we're going to come back to this in a minute here before we talk about the gist of it. But basically, all objects that have any mass whatsoever, and for our intents and purposes, everything has mass, means it's attracted to something else that has mass. So what that means is that everything in the universe is gravitationally attracted to something else. And there's a couple of things we can do to manipulate just how strong that attraction is. Namely, you can change the mass of those objects or the distance between the centers of those two objects. Now, the link I have posted here, highlighted in pink and purple, is a great resource to look at. It's a TV show called Science Court that was popular back in the 90s and 2000s. Kind of a humorous look at this with some cheesy animation that I think you're really going to enjoy. So if you want to know more about that, great resource right there. Basically, the gist is that we know from previous units that objects are pulled towards Earth. That makes sense, right? We have a force of gravity. It's the reason why we're not floating off into space. Is the reason you and I have weight. But what you probably don't know is that each of those objects also are gravitationally attracted to each other, like these two pencils, for example. They're both being pulled towards the Earth, but there's also a force of gravity that they have towards each other. This is where this comes in. All right, imagine instead of pencils now, we have these two circles or masses representing it. And that is the equation we're going to use. This is for the magnitude of the force of gravitation, okay? And you can see here that the force that mass 1 exerts on mass 2 is the same as mass 2 exerting on mass 1. So sounds a lot like the equal and opposite reaction from Newton's third law, right? And we have an equation there at the bottom where we have the masses are multiplied together. The square of the distance between the center of the objects is also in the denominator. One of the things we have to be careful of is that that radius or that distance between the two objects is the center of the objects. So you can have a very massive object that has a radius of thousands of kilometers. We really only care about the middle of it, so be very careful on that. And then that g in the front there is a gravitational constant, kind of like how we use pi as a constant in mathematics a lot. It's the same premise here. All right, that's a number right there. It's a number. I want you guys to know that it's a thing. It's got some crazy units, right? Because you've got some forces and you've got an area involved there and a mass involved there. So that's why you have such crazy units right there. That's what that G is right there. So my advice for you is that if you aren't comfortable with using scientific notation in whatever calculator you're using, we figure it out now because it's going to make life a lot easier if we've got a way to do that. So if you're curious of how that G came around, we didn't just pull this out of the sky. Henry Cavendish did this a long time ago, just before the 19th century, and it dealt with basically a swinging rod. And it was gravitationally attracted to these, and there were very precise measurements. He was able to figure out, based on the acceleration of the rod, just how strong that G was. And if you're interested in that kind of stuff, I highly recommend do a quick Google search on Sir Henry Cavendish. He's a very interesting fellow. Not just in scientific terms, but also his personal life. It's a neat experiment. So my suggestion for these kind of questions is going to be Desmos. All right, and to borrow a line from How I Met Your Mother, have you met Desmos? Because it's going to be one of your best friends. All right, if you click on that, it's going to really help you with using those scientific calculations instead of maybe doing all the work, but just forgetting to put in your calculator correctly. I would hate to see that happen. So I'm going to go ahead and actually click on that so we get a good look at Desmos. If you haven't used this before, for example, if you want to use the gravitational constant, you can use either this pad here, or you can use your keyboard, obviously. So if I wanted to type in the actual constant, I'd start here, and I click this button here to get my -11 in there, and you can see it shows up on the other side. If I want to multiply something, it's going to be a good idea to use some parentheses. All right, and let's just say I got a couple masses here of 2. I've got another one that's like 3. Of course, we're making these up. And then you can see here, if we're going to divide by, let's just say, a radius squared, you know, see how much nicer that is? And then for some of you that have graphing calculators, you have this capability. For the majority of us who are using scientific, this can get really messy in your calculator really quick. So Desmos is going to be a great tool here. And immediately you can see, without even hitting the enter button, your answer on this side over here. So I'm going to really suggest, if you haven't already, Desmos Scientific Calculator, going to help you out quite a bit. Okay, so an example over here, we got 2 dogs pulling each other. This little baby Chihuahua, isn't he cute? And this big Great Dane. They have a gravitational attraction because they both have mass, and we want to figure out how much that is. And the work is shown here before us. If you wanted to do that in Desmos, it's really easy. We do what we did before, except we've got 90 for one of our masses, and 3, and we got 10. And we can see we get the same answer right there. So see how much easier that was instead of trying to plug that into a regular calculator. Newton's third law and second law are still a thing, though. Okay, so we have to be careful with that. The force of one dog as opposed to the other one on the other dog is still the same. So the force of the Chihuahua on the Great Dane and the force of the Great Dane pulling on the Chihuahua are the exact same numbers. That's where Newton's law comes in. The second law says that each one of those dogs is going to feel that force a little differently. So that Great Dane has a much larger mass. And so if you solve F equals ma for acceleration, that number is smaller than for our little dog, the Chihuahua, right? That Chihuahua feels that acceleration more because he has less mass. So that same force is going to pull him with more acceleration. It's the reason why, these pencils are definitely being pulled on by the Earth. But the Earth is feeling the same force of gravity from those pencils. So that Earth is actually accelerating towards those pencils, not like that quick, right? But it is feeling it, all right? It's just that its mass is so huge, it accelerates such a tiny amount, where our pencils accelerate much quicker towards the Earth because they have a very, very small mass. Same force, because of Newton's second law, you feel those differently based on your mass. A lot of the questions we're going to ask you here in the upcoming quizzes are going to be based on the relationships within the formula itself. What happens when I manipulate certain parts of that equation? An example might be, if we double a mass or we triple a distance, those kind of things. My suggestion is going to be, because most of them ask you to compare it to the previous example, to just compare the variables we can actually change. Don't worry about the constant g, because g is always in there, and there's no point of you having to go in and type that in your calculator over and over again. So if you're asking about a relationship, I would not worry about that constant, because that's not a variable that we're going to be able to change. My suggestion is also going to be that you replace these variables in the equation, mass and the distance, with the change that you're asked to deal with. So for example, doubling the mass. Doubling is code for 2 times something. So we're going to replace one of the masses with a 2, right? Everything else will be left exactly the same as it was. There's no change. If it makes you feel better, you can imagine that M2 and that R are 1s, all right? And you're only going to record the thing has changed. So you've doubled the force of gravity because you have 2 times what you originally had. That 2 is left over, right? If we imagine the M and the R are both 1s, you have 2 times 1 over 1 squared, you got 2, right? Now, if it's on top, you're going to be, you would have doubled. If that 2 was left over on the bottom, it would be, you have 1/2, right? Same thing here. When you cut both masses in half, okay, so M1 and M2 are going to be affected. We'll change those to 1/2. And because they're multiplied, that's about 1/4 of what you originally had, right? So the new gravity is 1/4 of the original gravity. So you see how we're changing these word problems into basic multiplication of fractions. And I know for some of you that's incredibly scary sounding, but it's really going to help you save some time here instead of having to plug that into the equation every single time. All right. You triple the distance. So instead of changing the mass, we're going to be changing the distance. So that means those m's will stay the same. Only the distance will change, and we'll go ahead and solve that out. Remember, it's squared. Remember, it is squared, so don't just leave it alone as 3 on the denominator. All right, we're going to actually have to simplify that. So it is now 1/9 of the original magnitude. That's it right there. Now, sometimes we get a little diabolical, and we decide to combine some things. Okay, so if we triple the distance and double one of the masses, let's replace all the things that changed. So obviously R is changing, so we need to change R to 3, and we need to change one of the masses, either 1, to a 2, because that's double, right? So if we simplify this, we have 2 over 9, so we have 2/9 of the original gravity. Okay? So that's a simple way of comparing those relationships when you're multiplying or if you're decreasing those values inside that equation. And last but not least, we all have gravity. And if you've watched that YouTube link that I recommended earlier, you'll understand that reference. It's a pretty groovy song there at the end. Remember that we all have gravity, and we have an equation for that gravity that lets us predict the force between all objects. Till next time, see ya.